This is section 10.3, Further Identities. All right, so let's start with the double number identities. In fact, let's start with cosine of double A, double an angle. Well, the way we're going to get at this one is to remember that 2A means the same thing as A plus A, and we can use the cosine of a sum, just the two things happen to be the same, so that's going to be cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second. And of course, because they're identical angles, we can call this cosine squared A minus sine squared A. So that's our first double angle identity. They call them double number identities. I call them double angle identities. Both, I guess, are appropriate. Double angle identities is how I will probably refer to them. Okay, so that's our first one. And of course, as we've talked about before, anything like this that we come up with needs to be memorized. Or, as you're starting to see, maybe it would be easier just to know how to derive it like we just did and go through that process every time. You could certainly do that. So that's our first identity. Now, because of the Pythagorean identity, alternative form, if I wanted to, couldn't I replace sine squared A with, notice the parentheses, 1 minus cosine squared A? Isn't that valid? And so what I'm doing is I'm able to write this in terms of only cosine. There will be no sine in this one. So distributing and collecting like terms, that gives me 2 cosine squared A minus 1. So that is our second double angle identity, and it's an alternative form for the cosine of 2A. It could be the one we wrote first, or it could be this one. Well, there's one other possibility. I could instead have replaced cosine squared A using the Pythagorean alternative form with, I could have replaced it with 1 minus sine squared A minus sine squared A. And now notice this is now written entirely in terms of sine of A. There is no cosine of A anymore. And collecting like terms, you get 1 minus 2 sine squared of A. So that is the third and final version of cosine of 2A. And there are 3 of these, and we actually use all 3 for different reasons. And so these are all 3 needing to be within your ability to get and use. All right. So, now, let's do sine of 2A the same way. So I'd like for you to pause and see if you can figure out what sine of 2A is all by yourself. Okay, hopefully you thought of using A plus A to replace the 2A so that you can use the sine of a sum formula. So that's sine of the first, cosine of the second, keep the sign, cosine of the first, sine of the second. Now those 2 items are actually identical. The reversal, when you've multiplied 2 things, doesn't change the value. So I'm going to write them both in the order sine A, cosine A, and I have 2 of them. So I add them together and I get 2 sine A, cosine A. And that's our fourth double angle identity. And again, all of these are used. You will see them in calculus again, by the way. So don't neglect learning all of these identities, because most of them do come back to visit you in later courses. That's why we learn it in pre-calculus, is because we need them in calculus. Okay, so let's try tangent of 2a. Well, we seem to have a winning strategy here of thinking of 2a as a plus a. So we might as well stick with it. And tangent of a sum is tangent of the first, keep the sign, tangent of the second, divided by 1, change the sign, tangent of the first, times tangent of the second. And simplifying, we get 2 tangent A in the numerator divided by 1 minus tangent squared A. So that is our next double angle identity. So I'll write it over here in the list. Okay, so let's see what types of things we can now work on. So our first example, we're given that cosine of theta is equal to 3/5, and we're told that sine of theta is negative, and we're supposed to find several things. I'll list them out. Sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. Okay, so thinking about what we know, if cosine of theta is 3/5, which by definition is x over r, then we need to find y to find sine of theta. So I know that x squared plus y squared is equal to r squared. So y is equal to plus or minus 4. And for sine of theta to be negative, for y over r to be negative, given that r is always positive, that implies that y must be negative. And consequently, we'll keep the negative 4 and conclude that the sine of theta is negative 4y over r. Sorry, negative 4, which is y, over r, which is 5. Okay, so let's start finding some of these. Sine of 2 theta is, according to its identity, 2 sine theta cosine theta. And again, please make sure you're committing these to memory as quickly as you can. By substitution, sine of theta is negative 4/5, and cosine of theta was given to be 3/5. And so the final answer is negative 24/25. Okay, cosine of 2 theta. Well, we have 3 versions of that we could use. If I only wanted to use the given, cosine of theta is 3/5, I could use the one of those that has only cosine in it. So 2 cosine squared theta minus 1. is the one I want to use. Now, I could use the calculated sine theta in the original one we got, but using that calculated value might be dangerous if I happen to have made a mistake in finding sine of theta to begin with. So this is the safest bet, I think, because sine of theta is actually negative 4/5. If you used a different identity, you could get the right answer. I'm just saying this is the easiest because of what was given. Okay, so 2 times 3/5 quantity squared, then subtract 1. So that's 18/25, so negative 7/25. Okay, and tangent of 2 theta. Well, you may think, oh my gosh, now I've got to use that double angle answer for tangent. Well, I'm going to be smarter. I'm going to rely on something else that would work just as well. The ratio identity, or sometimes called the quotient identity, is the quotient of these two things, which we've already found. 2 theta, sine of 2 theta is negative 24/25, and that will be divided by cosine of 2 theta, which is negative 7/25, which simplifies to be positive 24/7. And that's that. All right. Now, you may recall when we verified identities earlier, I called it proving. And so I'm going to continue calling it that. And remember the transitive proof that we talked about. We're still going to use that. So prove the following. Cotangent of x times sine of 2x is equal to 1 plus cosine of 2x. Okay. Well, I need to pick a side that I think is more complicated. I think the left side is slightly more complicated because it uses 2 different arguments. One is x, the other is 2x. So I'm going to start always with a more complicated one if I can. Decide which one that is. That seemed redundant, but actually was grammatically correct. Just sounded weird in my head too. So I'm going to first start by using the double angle identity for sine to write 2 sine x cosine x. Then I'm going to change cotangent x into cosine x over sine of x. You might notice that the sine x and the sine x cancel each other out, leaving 2 cosine squared x. Oh, well, what's that? Well, let's look at the identity, because we know where we're headed is cosine of 2x. It's got to be part of our answer. Let's look for cosine of 2x. Oh, it's 2a up here. Oh, yeah. Okay, I see it. Do you see the second one here? An alternative form of that would be to add 1 to both sides. And so this is a true statement, an identity as well. It's just an alternative form. So that is viable as a substitution. So I'm going to take out the 2 cosine squared x and replace it with 1 plus cosine of double x, 2x, which is exactly what I wanted it to be. And so, therefore, I can conclude that indeed cotangent of x times the sine of 2x is really equal to 1 plus cosine of 2x. All right, very good. That one's done. So it is really important that you are able to see those alternative forms like we did in that last one. That last step is pretty important, and if you don't know the identities really well, you certainly probably won't be able to know those alternative forms easily. So make sure that you really learn the identities well. Right. So let's go on to the next page. We're supposed to simplify each expression as much as we can. So let's look at the first one. Cosine squared of 7x minus sine squared of 7x. I'm hoping you realize that this is one of the versions of the double angle identity for cosine. So cosine squared a minus sine squared a is equal to cosine of 2a. So this is going to be equal to cosine of 2 times whatever that argument is on the left side. And of course, that will be cosine of 14x. Okay. B. Sine of 15 degrees times cosine of 15 degrees. Well, that's almost the double angle identity for sine, except for it's missing something. So the thing it's missing is a 2 out in front. So I'm going to multiply in front by 2, but that's changed the answer. But only if I don't also multiply by 1/2, because 2 times 1/2 is 1. So that's a form of 1 I'm multiplying by. And it's perfectly valid to do this. So that the 2 sine a cosine a becomes the sine of 2a, and a here is 15 degrees. But then don't forget to multiply that by 1/2, which should be out in front. So that 1/2 goes there. It was all of 2 sine a cosine a that became the sine of the double angle. And so this is 1/2 times the sine of 30 degrees. Oh, we know what that is. Sine of 30 degrees is 1/2 times 1/2 is 1/4. There you go. Okay, now let's look at the next example. Find the values of the 6 trigonometric functions of theta if cosine of 2 theta is 4/5 and theta is known to be between 90 degrees and 180 degrees. Okay, so to find the functions of theta, we're going to have to go from 2 theta to theta. So one thought is I could use one of those identities for cosine of 2a that involves only one trig function. And there are 2 of those to choose from, and it doesn't really matter which one I choose. I think I'm going to use this one because I used the other one a bit earlier, if I recall correctly. So I'm going to use this one. I could have used, however, 2 cosine squared theta minus 1 instead. I just decided to use this one. So I'm going to solve for sine one step at a time. So I'm going to first subtract 1 from both sides. Then I'm going to divide both sides by -2. So now I know sine squared theta is equal to 1/10. So that means that sine of theta is equal to plus or minus the square root of 1/10, which is plus or minus the square root of 1 over the square root of 10. And then rationalizing, we get plus or minus the square root of 10 over 10. Okay, now, why did we need to know that theta was between 90 and 180 degrees? Well, that's going to tell us whether sine of theta is positive or negative, if cosine of theta is positive, negative, etc. So for all 6, we need to know the quadrant. So because we're in this quadrant, that means sine is positive. Okay, so we now know our first answer is sine of theta is square root of 10 over 10. Okay. Now, to find cosine, we have some options that we can use. I think what I'm going to do is I'm going to use this version, and it is still positive, by the way, and I'm going to call that y over r, because that's what sine of theta is. And so I'm going to let y be 1. So y is 1, and r is square root of 10. And I think I can find x now, because x squared plus y squared has to be r squared. And so that means that x squared is equal to 9, and x is equal to plus or minus 3. And in this quadrant, between 90 degrees and 180 degrees, the second quadrant, x is negative. And so now that we know x is, I'm going to rewrite these because they're kind of messy, I guess. We know that x is negative 3, y is going to be positive 1, and r is going to be square root of 10. We can now find all 6 answers. See, cosine of theta is x over r, negative 3 over the square root of 10, which rationalizes to be negative 3 square roots of 10 over 10. Tangent of theta is y over x, 1 over negative 3, so that's negative 1/3. Let's see, cosecant of theta is the reciprocal of the sine, and in fact, I'm going to go back to where I checked that in green and do the reciprocal of that. The reciprocal of 1 over square root of 10 is square root of 10 over 1, which is simply square root of 10. Secant of theta is the reciprocal of cosine. I'm going to go to the first thing I wrote, which was square root of 10 over negative 3. Just going to make that negative square root of 10 over 3. And then the reciprocal of tangent will give us cotangent. The reciprocal of negative 3. The reciprocal of negative 1/3 is negative 3. There we go. Next problem. In fact, why don't you try this one on your own first and see if you can do it. Write sine of 3x in terms of sine of x. Pause the recording and see if you can figure this one out by yourself. Okay, let's see how you did. I'm going to use an idea that we did earlier for the double angle identities when we first developed those. And I'm going to think of 3x as the sum of two things. And it doesn't matter which one you put first, but I'm going to make it 2x plus x. Now using the identity for the sine of a sum, that's sine of the first, cosine of the second, keep the sign, cosine of the first, sine of the second. So I want sine of x only. Of course, it's going to take several steps to get there. Sine of 2x, I'm going to use that double angle identity, is 2 sine x cosine x times the cosine of x that was already there, plus, let's see, cosine of 2x. I'm thinking the better one to use here, or best one to use here, is the one that has only sine in it. 1 minus 2 sine squared of x times sine of x. So 2 sine x. Without taking an extra step to write it, that's cosine squared x right there. And I'm going to use an alternative form of the Pythagorean identity. Cosine squared, which is what these two things become. Cosine squared is the same thing as 1 minus sine squared of x. That's that alternative form. Like I was saying earlier, you really need to know those. Okay, let's distribute the sine of x. So that'll be sine of x minus 2 sine of x cubed, or sine cubed x. So distributing here, it's 2 sine of x minus 2 sine cubed of x plus sine of x minus 2 sine cubed of x. And simplifying that, we get 3 sine x, combining like terms, minus 4 sine cubed x. Again, combining like terms. Okay, there's that one. Let's see, what's next here? Determining wattage consumption. If a toaster is plugged into a common household outlet, the wattage consumed is not constant. Instead, it varies at a high frequency according to the model W, which is the wattage, equals the square of the voltage divided by R, which is a constant that gives you an idea of the resistance of the toaster in ohms. Okay, V is the voltage, R is a constant that measures the resistance of the toaster in ohms, W is the wattage. Okay, so graph the wattage W consumed by a typical toaster when R is 15 and V is equal to 163. That looks familiar. Sine of 120 pi t. Yeah, this is what we used earlier in an earlier problem when we were talking about the voltage being alternating current. Yeah, I remember this one. And that was omega t, and we figured out that omega was 120 pi. Yeah, I remember it. Okay, so we're going to graph this W from 0 to 0.05. Okay. How many oscillations are there? Okay, here we go. So by substitution, the wattage equation will be 163 sine of 120 pi t quantity squared over r, which is 15. Oh, yuck. Okay, well, we'll get there. So let me think here. This is going to be 163 squared sine squared of 120 pi t over 15. Alrighty then. Well, this is a problem that the textbook authors put into this book, assuming that you would have a graphing calculator to do all of the problems in this book. And since that's not a requirement, this is not something I would expect that you could graph without help. So what I'm going to do is I'm going to show you what that graph looks like. Basically, this is what you would see if you had a graphing calculator to graph this. And this is T, this is wattage. Of course, because sine is squared, you know that that's going to give you a positive answer, or 0, times 163 squared over 15. All of the answers are going to be on the t-axis or above it because of that. Okay. And then the graph looks like this. Well, sort of. They're all the same height. Sorry, I'm not making that perfect. Wow, that made that pointy looking at the bottom. It wasn't supposed to be. Okay, and unfortunately, didn't plan well enough. This is the t-axis, and that right there is 0.05. Whew, sorry about that. So you would graph this on a graphic calculator, and it would look way better than this one does. By the way, since the largest value that sine can have is 1 and the lowest is -1, if you square that, that means that the greatest value you'll get for sine squared of something is 1. And so that means that the greatest wattage you can get, this is the greatest wattage possible, is going to be 163 squared times the greatest sine output when it's squared over 15. So that's, of course, 163 squared over 15, which, if you need a decimal form for that, it's about 1771.267. Okay, so that's the highest value right here, 1771.26. It's actually 2 and then 6 repeats, just to be exact. Okay, so how many oscillations are there? Well, an oscillation is a period, so it looks like we have 1, 2, 3, 4, 5, 6. So 6 oscillations. Is the answer, which you couldn't have done this without a graphing calculator, just saying. I'm going to add a question. What is the range of W? What's the range of the function W? Well, you can probably tell me just by looking at that. Once the graph is done, it's not that hard. The lowest is 0, and the greatest is 1771.26. to 6 with the 6 repeating. That's the range. Okay. There we go. There's the range. All right. So let me see what's next. Oops, we're out of room there. So let me move over. Sum. A little bit more. Okay. Go back up to the top. Go. All right. So let's see what else we have to do here. Oh, the product to sum identities. They're used in calculus quite a bit. You don't need to actually know this yet, but it's to find integrals of functions that are products of trig functions. And so these are really important identities. And so to develop them, and this is actually the way I don't memorize these, I just develop them. I'm going to take cosine of a plus b and say add it to the cosine of a minus b. And see what the answer is. So cosine of a plus b is cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second, and cosine of a minus b is cosine of the first, cosine of the second, change the sign, sine of the first, sine of the second, and I said to add those. And you may see that there you get 2 cosine A, cosine B, and that's all you get because the other two things are opposites and add up to be 0. So that's equal to cosine of A plus B plus cosine of A minus B. And to get it in the form that's useful for us, I'm going to divide both sides by 2 and switch the sides. So I'm going to get cosine A, cosine B by itself by multiplying both sides by 1/2. So that's going to be 1/2 times the quantity cosine of A plus B plus cosine of A minus B. And that's one of the product to sum identities. Okay. So you could subtract the sum and difference identities of sine and cosine and develop the rest of these. And so I'm not going to go through that process for all of them, but you could have subtracted instead of adding. You could have used sine of A plus B and sine of A minus B, add and subtract those, and you'll get all 4 versions of this. So these are the product to sum identities. Again, I think it's more important that you might not want to memorize these as much as figure out how to remember how to produce them, like we did that one up there. Okay, so here they are. Cosine of A, cosine of B, as we just did. So I have the cosine of something times the cosine of something different. And that becomes 1/2 times the cosine of the sum of those two different things plus the cosine of the difference of those two things. And believe it or not, that makes integration in calculus for that kind of problem super duper easy. Okay, if you have the sine of A times the sine of B, that's going to end up being 1/2 times cosine of A minus B minus cosine of A plus B. Okay? The sine of A times the cosine of B is 1/2 times the quantity sine of A plus B plus sine of A minus B. And then finally, cosine of A times the sine of B is 1/2 times the quantity sine of A plus B minus sine of A minus B. Okay, so there you go. Those are the product to sum identities. So let's see if we can do a problem that involves that. The example we have is to rewrite cosine of 2 theta times sine of theta as either the sum or the difference of two functions. So we're turning a product, cosine of 2 theta times sine of theta, into a sum or difference. So product to sum identity is the correct topic. And we need to first identify which of these is the one that's going to do what you want. And I think it's the fourth one, cosine of something times sine of something. So we're going to use that identity. So using that identity, that's going to be 1/2 times the quantity sine of the first angle, 2 theta, plus the second angle, theta, minus sine of the first angle, 2 theta, minus the second angle, theta. And then simplifying, that's going to be 1/2 times sine of 2 theta plus theta is 3 theta, and minus sine of 2 theta minus theta is theta. And then you could distribute that 1/2 if you choose to do so. Because that is considered simpler. Do all distributions to make simpler. And there's our final answer. That's now a difference of two functions. Now, we can derive another set of identities called the sum to product identities using those identities we just got. And without my telling you how to do that, I'm just going to show you what those end up being. These are the sum to product identities. So the sine of A plus the sine of B, that's a sum of two functions. And we're going to turn that into a product. And that becomes 2 sine of A plus B over 2 times cosine of A minus B over 2. The sine of A minus the sine of B is 2 cosine of A plus B over 2 sine of A minus B over 2. The cosine of A plus the cosine of B is 2 cosine of A plus B over 2 times cosine of A minus B over 2. That's cosine there. Okay, and then finally, cosine A minus cosine B will equal negative 2 sine of A plus B over 2 times sine of A minus B over 2. Okay, so those are the sum to product identities. So let's see if we can put those to use. Write sine of 2t minus sine of 4t actually that looks like 4t as a product of two functions. So looking at those four, which one of those is our best candidate? Well, it's the one where we have sine of something minus sine of something. That's the second one. So according to that second one, this will become 2 cosine of A, which is 2t, plus B, which is 4t, over 2, times the sine of A, which is 2t, minus B, which is 4t, over 2. Now we have to do a simplify. See, 2t plus 4t is 6t. 6t divided by 2 is 3t, times sine of 2t minus 4t is negative 2t, divided by 2 is negative t. And if ever you have an opposite of an angle in a trig function, you should always use the even odd identities. And the sine of the opposite of t is the opposite of the sine of t because sine is odd. That negative I'm going to pull all the way out to the front, making that negative 2 cosine of 3t times the sine of t. Using that even odd identity that we learned earlier. Okay, now the half angle identities is the next topic. They're also used in calculus when trying to get rid of the xy term from a quadratic equation of the form ax squared plus bxy plus cy squared plus dx plus EAY plus f equals 0, so that the type of conic it represents can be determined. And we'll talk about some of this a little bit later, the conic sections. But we won't deal with the xy term in this class at all. But this is used to do that. So let's look at the three versions that we have for cosine of a double angle. Okay, cosine of 2x. One of those is 1 minus 2 sine squared x, right? So what I can do is I can add 2 sine squared x to both sides and subtract cosine of 2x from both sides. I could then divide both sides by 2. So on the right, that'll be 1 minus cosine of 2x, all divided by 2. And then take the square root of both sides to solve for sine of x. Of course, when we take the square root of both sides. Please don't forget the plus or minus. Now that does not mean that you get two answers for every problem. That plus or minus, what it implies is that for some x's, the sign of that x will give you a positive answer. For some x's, the sign of that x will give you a negative answer. It depends on the quadrant in which x lies. So you'll either have a positive or a negative answer depending on where x is. That's why the plus or minus is there. It's for that. Now, if we were to take that and let 2x be replaced by a. And if you do that, that would mean that x would equal half of a divided by 2. So if we did a substitution, that would be the sine of the half angle, a over 2 is half of a, is plus or minus the square root of 1 minus cosine of 2x, which is what we called a, divided by 2. Okay, so make sure that radical is the whole fraction. So this is the half angle identity for sine. Okay, so that's our first half angle identity. Alrighty. So let's do a similar thing to see if we can find out a half angle identity for cosine. Another version of cosine of 2x is that it's 2 cosine squared x minus 1. So I'm going to solve this for cosine. That didn't look like cosine up there. I'm going to solve this for cosine. So I'm going to add 1 to both sides. Divide both sides by 2. I'm going to switch sides, by the way, because I'm really trying to solve for cosine, so I want it on the left side. So I'm switching side to the equation, and I'm dividing both sides by 2. And cosine of x is therefore equal to plus or minus the square root of 1 plus cosine of 2x all over 2. By the way, I want to say something about a step that we used now twice. This right here is also an identity all by itself, as is this one. And these I'm going to call power reducing identities. It's not in your book. It's not something that you're supposed to know yet, so I'm not really wanting you to stress about this one. But the power reducing identities are also used in calculus quite often. And it lets you turn a sine squared of something or a cosine squared of something into a cosine of a double angle without the square there. So you're taking the square away by using this identity. Notice that if you're going to use that identity, the cosine squared of x would become 2x, so the angle gets doubled as you reduce the power. So that's kind of interesting to know. But sorry, I got a little bit sidetracked because that is an important one. So again, I want to let 2x equal a, which of course means that x is the half angle of a divided by 2. And that means that the cosine of x, which is a over 2 by substitution, is equal to plus or minus the square root of 1 plus cosine of 2x, which is what a is, all over 2. Now you might notice that those two identities are almost the same. The only difference is a little subtraction or a little addition in the numerator under that radical. So that's really the only difference between those two. So that's the half-angle identity for sine, that's circled or boxed in blue, and the half-angle identity for cosine. The tangent, I'm not going to develop this one for you. I'm just going to tell you what it is. There are 3 versions of this. One is to use the idea that it would be sine of a over 2 divided by cosine of a over 2. And after you simplify, this is what you would get. Which, if you think about it, you could probably see how that would simplify to be this. The problem I have with this one is, again, you have to figure out where a over 2 is. And that's true for all of these. You have to figure out where a over 2 is. And wherever a over 2 is tells you whether the answer is positive or negative. Because once you're in the correct quadrant, you have to figure out, well, is the sine there going to be positive or negative? Is the cosine there going to be positive or negative? Is the tangent there going to be positive or negative? And so that's kind of a nuisance to have to do that. And that's why I don't like this version of the half angle for tangent. The one I prefer is one of 2. There are 2 versions of it, and they are both good. The reason that you really need to know both is that, remember, you have to know them backwards and forwards. What if I gave you the sine of something over 1 plus the cosine of something? Would you realize that that would become tangent of half of that something? Yeah, so that's a good one. Notice there's no plus or minus here because the sine of a and the cosine of a in that formula automatically give you the correct positive or negative answer you're looking for. The other version, the third version of the tangent of the half angle is 1 minus cosine of a over sine of a. And again, needing to know these backwards and forwards, you might need to know that 1 minus cosine of a over sine of a is also tangent of half of a, or a over 2. So, what in the world is this used for? Well, if I ask you to find an exact value, that means don't pick up your calculator, which means you probably are supposed to use an identity. What's the cosine of pi over 12? Now, I know that you could use a sum difference identity for this one. But if I said, okay, but I want you to use a half number or half angle identity to do this, you're going to have to figure out that pi over 12 is obtained by taking some angle and dividing it by 2. So what angle divided by 2? What angle divided by 2 would equal pi over 12? So you could figure that out by multiplying both sides by 2, and that would give you pi over 6. So this would be pi over 6 divided by 2, which is the same thing as pi over 12. So using the identity up above for cosine of the half angle, this is going to be plus or minus. I'll write which one it is here in a second. Oh, I don't have to. Where's cosine? I'm sorry. Where's pi over 12? Well, 1 pi over 12 is a positive angle that's not very big. It's about that big. And with it being in the first quadrant, cosine is definitely positive. So you don't need to write a positive when it is positive, but I'm going to write it this time just to remind you that we got that from thinking about where pi over 12 is. Okay, and then in the final answer I won't write that plus. All right, so this is supposed to be 1 plus the cosine of the angle that you've divided by 2, namely pi over 6, divided by 2, which is the square root of the cosine of pi over 6 is square root of 3 over 2 divided by 2. And I notice that under that radical I have a complex fraction. And the common denominator of all the little fractions is 2, because there's only one fraction that's small in this one. So multiplying by that form of 1 in the numerator denominator gives me the square root of 2 plus square root of 3 all over 4, which is the square root of 2 plus the square root of 3 divided by square root of 4, which is 2. You've probably never seen an expression that looks like that. The square root of a number plus the square root of another number. So you have a radical under a radical. It's very different from some of the things you've seen. So you're going to see some weird looking answers. But that is the correct exact answer. All right, so let's look at the next example.